Um, all right, well, it's 8 o'clock. Let's get this show on the road. So, hopefully you guys all saw my Canvas announcement from mañana, or no, yesterday. Mañana's tomorrow. What's yesterday? What is it? Oh, yeah? Oh, well, yeah, that makes sense because it's here en français. That's quite logical. So, um, right, so we all saw my announcement, right? So how are we going to kind of finish things off for the semester? Because we got basically 2.5 weeks more of class, right? We got this week of class, we got next week of class, we have Monday, Tuesday, the week after, and then Wednesday there's nothing, and then Thursday, Friday, and then the following Monday, Tuesday is finals. Da da da. Right. So when is our final? Huh? Well, when, not what. Yeah, that's Thursday night of finals week. So the very first day, we get it out of the way, right? Huh? Darn it. What do you mean? No, because then you guys would all be wrenching to go home. Trust me, I've played this rodeo. Well, that's your problem. Yeah. So, although, from what I understand, Dean Welch is like, you guys, GTFO, right? Like he's changing the locks GTFO. That's pretty hardcore GTFO, right? So, anyway, so, um, right. So we'll do the game jam. So the rhythm for the rest of the semester is right. We're still working on this machine code stuff. You guys are dutifully working on your awesome game projects, right? And have made amazing things so far, right? Okay. All right. So Friday afternoon, at, I guess 5 o'clock, whatever. Um, you guys will need to upload a link to your project to Canvas. Okay. And all three of these things, I think you can share links to it rather than um, an actual file. Okay. And there'll be three different assignments, and I'll assign the right assignment to each of you. Um, so there's going to be one that's for those of you guys doing Minecraft, one for those of you who are doing regular Scratch, and one that are for those of you who are doing Make Code Arcade. And the reason I'm going to split it up like that is because then when you guys do the peer review over the weekend, it doesn't make sense for you. I mean, you could, right? But it makes more sense for you to review somebody who's doing the same kind of coding that you are, because that way you'll actually be able to look at the code and know what's going on. Okay. Um, so that's why I'll split it up like that. And so I have a list of what everybody told me they were doing. We should probably verify that that's correct. Um, so what you'll see later today or tomorrow, whenever I get them put in, the different assignments. You'll only see the one that's assigned to you. So if that doesn't look correct, like I put you on Make Code and you were actually doing Minecraft, just let me know so I can assign you to the correct thing. Um, okay, so we're going to do basically 2 cycles worth of that this weekend and next weekend with the peer review. So you'll upload your thing. I'll have Canvas basically randomly assign you guys to review each other's stuff. And then you'll do that through Canvas. It's pretty foolproof. So we'll do that this weekend and then the second round of it next weekend. Next week during class, basically what I want to do is, well, not have class. And on each of the 3 days, spend about 5 minutes talking with each of you, right? So I'll assign you guys to a day. And then on your non assigned day, basically it's just work time, right? Time to work on your projects and or sleep in and or whatever, but you can't say I didn't give you time, right? So anyway, um, yeah, and then of course we won't have an actual exam during the final, but we'll have the the game jam thing. And roughly speaking, I'm going to estimate that that'll take us about 2 hours to do, uh, assuming that the tech all goes okay. So we'll start right at 6, and I'll come up with some sort of schedule. Um, the only thing I would suggest is that, well, two things. One, if you can, we don't all have to be in the same place to do it, right? And if we all are in here with our laptops going, the Wi-Fi is really going to get overloaded. Okay, so you can go wherever to do it. My suggestion would be to go someplace where you can, if possible, plug into a wired Ethernet connection, or use a like one of the computers in the library or something that already has an Ethernet connection, so that you can will have stability in that sense. And what we'll do for when I do the meetings with you guys next week is that we'll do them over Discord. And the benefit of that is that you guys will get used to sharing your screen on Discord. So if you go onto the Canvas site, up at the very top, it's got the link to my Discord server and a bunch of other stuff. So get the Discord desktop client installed, join my server, and then what you guys will do is basically share your screen or stream within that, and then I'll take that as an input, pipe it into OBS, and that's what goes out to Twitch. That's what the folks at, well, I told you guys about the Unreal Engine webinars that I went to. Yeah. Okay. In fact, actually, let me just show you guys one of them because it's really cool. What some of the stuff they did. So let me open up Safari here, and let's see. Um, Now let's see. Where did they do it? Here it is. I think this is it. Let me make sure this is the right thing first. Yeah, here it is. So this is how they did it, right? So they had everybody there over either Zoom or Discord, and then I'm not sure how they got the um, things lined up. I've got the audio turned off, so don't worry about that. Okay, so then this is the first student project. Let me full screen this. And at in a minute they realize that the name cards are still up and they take those down because we're all banging in the chat like take the name cards off. So they worked on this over the period of I think a year to a year and a half. So this is not like the kind of thing that you could produce in a couple weeks. In particular, I think they designed most of these assets themselves. So the shield, the pot with the steam coming out of all of that stuff, right? So, yeah, so students made this, right? It's pretty crazy. Um, it's like it would maybe be the first 30 minutes of a video game, right? So I think this one was like a 2 or 3 students that did this. There were some other ones that they showed that were more fully fleshed out, but they also had much bigger teams. Um, so, you could imagine that this would be the very start of, some PlayStation game that you guys buy, right? Um, and so this is all done in Unreal Engine. Um, yeah, so like that point, it cuts to a cinematic, right? So the player controls are disconnected, and then now the player is back doing it, and right, so he has to realize, oh, there's this cave over here, and right. I mean, but this looks like Yeah, okay, so there's all their code, right? Sort of organized into, they color coded it for different time periods of or areas within the game. But like this looks like Zelda Breath of the Wild quality, right? Even though it's the first basically 20, 30 minutes of a game. So um anyway, so they did that and I'll skip over, but then they showed off, another one. Let's see where that was. Here's another one that they showed off. Oops. Um, which is a little bit more cartoony in its art technique, but it's kind of like a hack and slash kind of thing. Um, so yeah, so this was my inspiration for doing this. So now, obviously, are you guys going to be showing off stuff that looks that good? Of course not, right? Like, it may be fun, right? But there's no way it's going to look like that. I mean, that's using a AAA game engine. So anyway, so that's where I got the idea for it. And given that we have to do all this so much crap online nowadays because of freaking pandemics and stuff, um, I suppose it's more fitting then that we do something kind of fun. So I don't know. Share the link with your parents. Don't share the link with your parents. Uh, I'm sure I'll get a bunch of alums and stuff, and hopefully they'll be on the Twitch stream being like, "Awesome job, Cole. That's a sweet game," right? Instead of this sucks, right? So yeah, no, no, it should be fun. So anyway, in the past, actually, we've done this a few times, and it actually was kind of fun. We went to the Carnegie Museum, which is the local history slash science museum here in town, and did this on like a Saturday afternoon, not live streamed, but then like kids came and um, the best part was, so I think this was 3 or 4 years ago I did this. One of Professor Hartnett's sons, so they both come, and his elder son starts going around to all of the projects and being like, "Oh no, 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 you shouldn't have done it that way." And he opens up the code and starts changing stuff, and it's like working 10 times better. And the students are all sitting there like, so yeah, that was pretty epic. This 9-year-old child fixing everybody's code. So anyway, all right. So let's get back to the Brookshire stuff. So last time what we looked at was the program to do subtraction, right? And how did we have to do subtraction? We had to do it by means of adding a negative, right? That's how it all works in two's complement. And so then the question was, how do we make the dang machine do it, given that there is no magic subtraction operation? Okay, so what was the solution? Well, instead of doing 5 minus 2, I'm going to do 5 plus negative 2, right? And then how do I compute negative 2? Well, I start with 2. How do I negate a number in two's complement? Just on paper, how do I negate a number? Well, that's how I make the computer do it. But on paper, what would I do? Flip the bits and add 1, right? So how do I make the computer flip the bits? I'm going to XOR it against a bit pattern of all ones. Okay, so, and I want to stress this, it's not just that I'm using XOR, it's that I'm using XOR and the pattern of all ones. Okay, so it's really a two things together. Um, so that flips all the bits, and then adding 1, well, that's easy. You just add 1. And that gets you then, therefore, the two's complement negative. And so then if you add that to the original number, then of course you get the result of the subtraction. So we did here 5 minus 2, and shockingly, we got 3. Everything was good. Okay, so, well, let's do something else. So, what's true about all positive numbers in two's complement? For with 8 bits, say. The far left bit is a 0. Okay, um, and also the number 0 has a far left bit of 0. That makes sense, right? Um, Okay, but then all negatives have what as their far left bit? They have a 1. Okay, so let's write a new program that basically can load in a number and detect whether or not that number is odd or even. Or sorry, not odd or even, positive or negative. Yeah. Okay. All right. So let me make a new file here. Okay. So first thing I'm going to do is I'm going to write this in sort of high level syntax, sort of like Python. Okay. So I'm going to write it Python-ish. It obviously won't work as Python code because I don't mean it to be full proper Python. I just mean it to be kind of the idea of what we want to do. Okay. So load a number from memory, and let's say that we load it from cell FE. Okay, it's got to be somewhere in memory, so I just choose to put it there. Okay, and then what we're going to do is something like this. If number is positive, write 01 to cell FF. Else, write, say, FF to cell FF. And let me put pounds, pound signs there. Okay. All right. So that's basically what we want to do, right? Now, in a high level language like Python, you could do something like this, right? If num is greater than, or sorry, not 1, 0. Okay. Or maybe better put, if num is less than 0, do something, otherwise do something else, right? So you can just type less than, and that's the end of it, right? Can we do that on our machine? No. Okay, so what we have to do is we have to recast the question of being positive or negative in terms of something being equal to something else. Okay, this also means that we need to talk about conditionals. Okay, because we've got the word if here. Okay, so first thing, let's just figure out. So if I hand you an 8-bit number, how do you tell whether or not the thing is negative or not? You look at the far left bit, okay, which is actually the last bit, but whatever, it's an order thing. Okay, right, it's the most significant bit, not the least significant bit. So you look at the far left bit, and if that bit is a 1, you know the number's negative, and if it's not, then you know it's not negative. It's either 0 or a positive. Okay, so what we need to do is figure out how can we get that far left bit sort of stripped out of a number, because we don't care about the other 7. We only care about the first, the far left one. Okay, we don't care about the remaining ones. All right, so the first thing I have to do is I need to load my number into memory, or from memory into a register. Okay, so where should I put it? Well, I can put it anywhere in, which register do you want? How about register number 1? Okay, because remember I think I said several times, thou shalt not use register 0. We will use it later today, but until now, don't use it, okay? All right, so I need to load into register 1 FE, okay? So what will that operation do? Okay, load what into register 1? What's in there? Whatever number is in memory address FE, right? Now, is that the number FE? Not necessarily, right? So we're saying which mailbox number to go to, not what the contents are, okay? All right, just want to make sure to reiterate that. Okay, so now the number that we're working with is in a register, okay? And what we need to do is figure out how can I strip out the far left bit. Okay, so let me just take an example negative number. Well, all ones is negative, right? That's actually the representation of -1. Okay, so how could I strip out that far left bit? Now, I'll give you a hint. There's 2 things we need. we need to use a logical operation, and we need to use a bit pattern of your choosing. Okay, so like how did we flip the bits? We used XOR with the bit pattern of all ones. Yeah? Here, we need a logical operation, and there are 3 to choose from, right? And, or, and XOR. And we need a bit pattern, and there are 256 of those to choose from. Okay, so roll the dice. Maybe think about it for a minute. Which logical operation and which bit pattern is going to do the job? I need to get like the Jeopardy music here so I could, although I'd probably get like copyright striked or something. Huh? I know, right? I'll lose all the Twitch monies. Okay, so maybe sketch it out on paper, think about it. This is the part where you guys like do things, right? When your professor says, why don't you guys think for a minute? Instead of just sitting on your ass or collective asses. Kids these days. I mean, I know it's 8 in the morning, but give me a break. Also, we haven't gotten any spam lately for buying followers. Of course, it helped that I added Big Follow's Starcom to the list of forbidden terms in the chat. So, yeah. Yeah, so you need a bit pattern and a logical operation that can strip out basically just that far left bit, because that's the dude we care about, right? We don't care about any of the others. Okay, so 3 logical operations to pick from, and, or, and XOR, and obviously, therefore, then 256 bit patterns to pick from, right? You got a pretty good chance of picking the correct logical operation. The bit pattern, however, you really have to think, right? Because your odds of picking one of those 256 bit patterns at random is not good. Better than playing the lottery, but still not great, right? And oh, hint, don't play the lottery. Where I'm from, I describe it as it's a tax on people who are bad at math. Oops. Let's see if anybody in the chat can figure it out. Monsieur Sanchez or Farden, good morning or evening, whatever. All right, we have any guesses? Mr. Early? No? The peanut gallery over there? All right, let's see if Owen with the 360 no scope. No? You don't have to know machine code. All right. First off, what operation do you think we need? And or XOR? Ah, it's actually and here. All right. And the bit pattern we need is that one. Okay. Hey, you should go buy a lottery ticket. Yeah? Yeah, okay. Okay. Well, so it's and though, not plus, right? Plus is a different operation than and, even though we in speech sometimes say and when we mean plus. Okay, so bitwise logical and. All right, under what circumstances will the output of and be a 1? Only when both inputs are 1, okay? And otherwise, it'll be a 0. Okay, so by putting zeros in 7 of the positions, what am I guaranteeing that those output bits will be? All zeros, okay? And why do I make that happen? Do I care about those bits? No, I could give two shits less about them. Oh, pardon my French, I'm on the internet here. Whoops. So, none of you guys have had me for other classes before the pandemic, but let's just say that I used to use much more colorful language, and then I started streaming on Twitch, and then I realized, I probably shouldn't do that. So, yeah, anyway. Okay, so we don't care about the 7 right-hand bits. So if I and against 0, it just destroys them. Okay, which bit do I care about? The far left one. And so I put a 1 in that position because I do care about it. Okay, so what are the two possible outcomes when I do this and? If the original bit, or sorry, the far left bit is a 1, what do I get for the far left bit here? A 1, and then the other ones are all 0. Okay, or if the original number had a, oops. Okay, so I've put stars there because do the 7 bits to the right, do they matter? No, they're going to be 0 after I do this anyway, so who cares what they are, okay? But if I and a number that has a leading 0, what do I get? All zeros. Okay, so by loading in this bit pattern of 1 followed by all zeros and anding it against my number, I either get all zeros or I get 1 followed by 7 zeros. Question. Ah, logical and. Yes, yes. It does it bit by bit. Okay, so it's going to do it and it's going to say, all right, this bit of the first number and the corresponding bit of the second number and those. 0, right. It's still 0, right? So who cares, right? So, yeah, and that's why I chose and rather than XOR or, okay? Because I don't want to flip the bit. I just want to strip out the one that I care about. Okay, in this case, the far left-hand bit. Okay, so what are the two possible outputs from this game? I either get all zeros or I get a 1 followed by 7 zeros. Okay. Okay, so what are each of those numbers in hex, by the way? Well, all zeros is just 0, 0, right? That's easy. What about 1 followed by all zeros? Huh? In hex. Nope. FF is all ones. Thank you. 8, 0. Okay. So we either get 0, 0 out of this or we get 8, 0 out of this. Okay, and that therefore gives us the basis for making a decision. Okay, so either the number is 8, 0 after we do this, or it's not. Okay, all right, so this brings us then to the one operation we haven't really talked about yet, and that would be opcode B. Okay, so what does opcode B do? Well, first off, its syntax is jump, then that's the mnemonic, okay? Then we need to specify a register and we need to specify a memory address. Okay, so what this will do is if register R, whichever one you specify, is equal to register 0, that's either true or false, right? Then it will change the program counter to be the value that you specify, okay, which is a memory address, which means we literally jump to a new location in memory to load in the next instruction. Okay, hence the name. Okay, does that kind of make sense? The idea, anyway? And implementing it's another matter. Okay? All right, now, this is why I told you never to use register 0 except now, because we always have to compare a register against register 0. Okay, and so because of that, we need to leave register 0 used not for anything else, but only used for doing these comparisons. Okay, because we always have to compare against register 0. Okay, does that make sense? Okay, so I need to load in a bit pattern to register 0 to compare against. Okay, what would be the two choices in this particular situation? I could either load in all zeros or 1 followed by all zeros, which is 80 in hex, right? Either one will do. We just have to make a choice, and the choice that we will make will subsequently affect our code. Now, we have to load in 80 anyway, right, in order to do the ANDing. So why don't we go ahead and just put that in register 0, okay? All right, so my second instruction is going to be that. Okay, so I'm going to load register 0 with the bit pattern 80. Okay, now I need to take the number that's in register 1 and I need to AND it against the number in register 0, and I need to put that answer someplace. Okay, where should I maybe put that answer? How about register 2? Okay, and so which operation am I using here? Which one am I doing here? This one. Oops. Dang it. Okay, this one here, right? I'm going to AND registers what and what together? 0 and 1, and where am I putting the answer? Hmm? Oh, I'm not doing the comparison yet. I'm just doing the ANDing. Okay, now let's remember the syntax here, right? In most of these operations, what do you specify first? Where it's going, right? The destination. That's not true about all of them, but it's true for most of them. Okay, so you've got to be very careful with the order here, because if you get the order wrong, woe unto thee. Nothing at the moment. Well, okay, so what's in memory cell FE? Whatever number we pick. Right. Random number of our choosing, but okay. So, all right, so I've done the ANDing, and now I need to, so let me come down here and let me start putting, let me put some extra info on the left here. Okay, so what am I putting on the left there? 00, 02, 04, and so on. How many bytes does each instruction take on this architecture? Exactly 2, okay? So these are going to be the memory addresses where I put stuff, okay, where I'm going to actually put these instructions. And we're going to need to keep track of that in a moment. Okay, because the next instruction is going to be a jump. Okay, which register has the result of the AND in it? Register 2, okay? And I'm going to compare that against register 0. Okay? Because the jump command always compares against register 0 in our architecture. Now, on a real architecture, you don't have that restriction. You can compare one register, any register, to any other register, okay, which is nice. On our particular architecture, you can only compare against register 0. Is that a little limiting? Yes, but c'est la vie. Mm-hmm. Yes. Uh, because it doesn't. I know. Right. Um, yeah, the move instruction doesn't either. You notice it's in backwards order from what you think. So Cole's question is, why is it that I'm not putting the memory address first here? And it's because that's not how the jump instruction was designed. And you can't blame me for this one. You have to blame old Brookshire. Okay. Um, yeah. Okay. So where do we jump? Well, I need to jump to a memory address, but I don't know where to jump yet because I'm not done writing the dang program. Okay. So what we're going to do is basically write it and then rewrite it. So sort of like rough draft, final draft kind of thing, right? Same idea. Okay. So what should we do if the result of register or what's in register 2 and what's in register 0 are the same? Okay, under what circumstances would they be the same? The original number was negative. Okay, what do we want to do in that case? Okay, so what do I want to do in the situation that the number was negative? What did we choose as our sort of output? Well, no, that's not what I meant. I'm sorry. Okay, so the number is either positive or negative. What did we write up in our pseudocode that we would do? Okay, if the number's positive, we'll write 0, 1. And if the number's not, we'll write FF. Okay, so if the contents of register 2 and 0 are the same, then that tells us we have a negative number in this case, right? So what is the set of instructions that I need to do in the situation where I have a negative number? Well, the first is I need to load what? I need to load a register with the bit pattern FF, okay, because that's what I picked. And then I need to write that to where? Cell FF. Okay, and then what do I need to do after that? Am I done? Yeah, I can just hold. Okay. What about if the number is positive? What do I need to do there? Load register 3 with, okay, and then store that where? Also in cell FF, and then halt. Okay, so, question? Ah, those are going away in a moment. Okay, so where I've written pause and neg, those are labels. Okay, so think about these as like rough draft instructions that don't actually exist, and I'm going to pull them out in a minute. Now, in real assembly languages, you can do things like that. They're called labels. Um, and I think when I showed you guys some of the real assembly in my little Linux install last week, it has labels all over the place. Okay, for good reason, because it helps you keep track of subroutines. Okay. Okay, so do you guys accept that those are the two things that would happen under the two different circumstances of if we have a negative number or we have a non-negative number? Yes? Okay. Now, here's the thing about the jump instruction. So the jump instruction either does or does not happen, right? If it does happen, we would jump down to here. If it doesn't happen, then what do? We just go to the next instruction. Okay? All right, so this positive and this negative thing, I can now delete. Okay? But what's the next instruction's memory address after 06? It'd be 08. And then what? Ah, you fell for it. Right? Rip. Okay, why is it 0A and not 10? Because everything is in hex, right? Because there are 10 types of people in the world, those who understand binary and those who don't.
No bullying.
No bullying? It's not bullying, it's character building.
Yeah.
Okay. Okay, what about the halt command? What's after OA? Thank you for the recovery. Okay, after 0C, it would be 0E. And then now what, Cole? Yeah, thank you. And then finally, 1, 2. Okay, so let me copy and paste this down here. Okay, and all right, so where is the first instruction of the negative routine? Sitting in memory cell 0E. Okay, the jump is in memory address 06, right? But where is the first instruction that we would do if the number is negative? It's down there in 0E. Okay, do we all buy that? Yes, no? Okay, 0. So what that means is where I have the word or the symbol neg here, I'm going to change this to 0E. Okay, and this will take me to right there. And then I'm going to get rid of that, and I'm going to get rid of that, and I now have a complete program. Okay, well, not quite. What do I have to do to finish this? Well, I've got the halt commands. That's cool. Well, this is all assembly. I have to change this into machine code, right? We've got to assemble our program, which means we got to do all this opcode nonsense. Oh, that's fun. All right, so what's load 1 FE? 1 FE 2080. What's opcode? Which opcode is for and? How about 8? Destination 2, input 01, jump B2OE. Load 2301 33FF C000 23FF 33FF C000. Okay, now you wonder how I did that so quickly? Well, partly because I've been teaching this for like 6 years now, and so I have all these opcodes memorized just because I've been doing it long enough. But if I didn't have them memorized, if only there were a table on the left-hand side of the screen that like told us what goes where. Wouldn't that be great? Yeah? Is it too early in the morning for bitter sarcasm? No? Okay. It's cool. That's cool, Cat. That's cool. Yeah. Okay. So what we just did then, right, to take the instructions and generate them as that sequence of numbers, that was the actual act of assembling. Okay, which on a real computer, a program does that for you. Alas, that program does not yet exist because I haven't written it yet. Sorry. So that means you guys get to do this by hand. Isn't that great? Yeah, it is character building. All right, so the next thing I need to do is basically just put all of this in a big long sequence. So that part I'm just going to copy and hope I don't make any typos. and I'm good. 33FFC00. Okay. And then I'm going to take this, right, which is basically just all the commands just strung together. Okay. And I'm going to go over to my web browser and I'm going to go to Joel's Brookshire emulator. And then I'm going to take and paste that stuff after the hash mark and then refresh the page and notice now what's in memory. Yeah, it worked. It's all, well, I haven't run it yet, but my code is all in memory, right? So we Gucci there? Okay, so let's run this thing and make sure it works. Okay, the first thing I have to do though is we load in a number from this memory cell. So let's pick a couple of test numbers. Give me a positive number in hex. 3A is definitely positive, and in fact, it's equal to 58. If you hover your mouse over it, it shows you the decoding of it, which is kind of handy. Okay, there's one problem though. The float one is wrong. Okay, well, or maybe better put, when we talked about floats, we talked about that hidden one. Yeah, the one that you get to assume because we're doing everything in binary. Brookshire's book does not talk about the hidden one. And so his floating point decodings don't have the hidden one. And so if you use this to decode a float, you'll get the wrong number. Okay? Because we did it the proper way with the hidden one. Okay, in my humble opinion. Okay, so let's execute this thing, but we'll do it step by step. Okay, so step one, start loading in the numbers. Okay, so 11FE loads register 1 with whatever's in memory cell FE, which is in this case the value 3A because that's what Cole picked. Okay, great. Next, we're going to load register 0 with the bit pattern 80. There it is. We're going to AND the result of register 0 and 1 and put that answer in register 2. Okay, and what is the result of ANDing 80 against 3A? All zeros, right? Because Cole picked a number that wasn't negative. Okay, so now I'm comparing registers 2 and 0. Are they the same? No, they are not. Okay, and so what do I do if they are not the same? I just move on to the next instruction. The jump doesn't get triggered. Okay, and I load in 1, I store it to memory, and I halt. Okay, so what did this program tell me? That number was not negative, it was positive. Okay, what about, give me a negative number in hex, Cole. A3. The first place has to be 8 or higher, right? So that the leading bit is a 1, okay? So A3, which corresponds to negative 93. Okay, so let me run that one. Right, and this time what should get output? FF. Ba-bam. It's almost like we know what we're doing. Well, okay, so is that pretty cool? Yeah? We just did conditionals. Guess what we'll do next time? No, this thing is not capable of doing recursion. Okay, fortunately for you guys, because recursion is a mind trip, right? However, what was between conditionals and recursion when we were doing this in pseudocode in Python? Loops. We can do loops. We'll do loops next time. It'll be glorious. Yeah? All right. Have a good rest of your Monday. I am way too chipper.